Hello everyone, welcome to lecture 8 on Mechanics and Materials 1. This is our second lecture on the topic stress, and we talk about the section 1.6 of chapter 1 of the Hibbeler book, and that basically is our last lecture on stress and our last discussion on the first chapter of the book. We begin this lecture by looking into two exercises that remained from the previous lecture, and then we talk about new topics afterwards. So the first exercise is similar to problem 1.8 on page 28 of the book. A bar is given in this exercise. The bar has a constant width of 35 millimeter and a thickness of 10 millimeter. Determine the maximum average normal stress in the bar when subjected to the loading shown in the figure. So you have this bar and you have the loadings, the external loadings as shown in the figure, and you are asked to calculate the normal stress in the bar and also judge where is the maximum normal stress. So we start by cutting the structure basically into different pieces and see what is the normal force at each piece, and then by dividing that normal force by the area we calculate the normal stress, and then we can compare those normal stresses to find what is the maximum stress. So for instance, we can start from the left hand side. If you start from the left hand side and you cut the part AB somewhere in the middle, then if you think, for instance, on this section, then you can imagine you should have a normal force here that must balance the force at A. So that's what we have here. And basically that tells you that the normal force, and that's the internal force, must be 12 kilonewton. Okay, so the unit is kilonewton. And also remember, it would have been the same if you cut it from the other side. So basically, if you cut it like that, you would also get a force 12 kilonewton, which would be basically the reaction of the 12 that you have here. So basically from A to B, the normal stress is 12 kilonewton. And then again, it has a plus sign in the sense that it shows that the member is under tension. Then we do exactly the same thing, but this time we cut it somewhere between B and C. And if you do that, then for instance, you look into this section and you know that you would need a normal force to keep the member or to keep this piece in equilibrium. And basically you have a force 18 here, you have a force 12. That tells you that the normal force must be 30 kilonewton. So the normal force between B and C is 30 kilonewton. Finally, you cut the structure somewhere here between C and D, and then again, you look at it exactly the same way. So if you look at this piece, this long piece, you can see that you have a force of 12 at the end. You had 18 at B, and then you have 8 in the opposite direction at C. So basically, you know that this force N must be 22 kilonewton to keep the member in equilibrium, or to keep this whole piece in equilibrium. Also, again, pay attention that we draw the N in the same convention, or according to the same convention that we use for the extension. So plus here means that it's a tension. But more interestingly, you can see if you looked into this other cut, then this would be your N. And also basically by looking at this one, you could have seen that N must be also 22 kilonewton. Okay, so basically it doesn't matter if you cut it from the left or right, you should always end up with the same conclusion. So for these types of problems, we usually draw this type of graph. And then in the x-axis, you have your bar or the different points on the bar here or on the rod. And in the y-axis, we are showing the normal force. Okay. And then again, remember, this is internal force. Okay. So if you do that, you can see that from A to B, the internal force is 12. From B to C, the internal force is 30. From C to D, the internal force is 22. So obviously, the maximum internal force would be between B and C. So N is maximum between B and C. Now, we know that the cross-sectional area for all the sections is identical, and that tells us that where you have the maximum normal force, then you have also the maximum normal stress. So if you look at the cross-sectional area, the problem tells you that you have the dimensions 10 and 35 millimeter. So the area would be 35 times 10 millimeter. It's a rectangular cross-section. And then basically you divide the normal force by the area, you end up with the stress. So the maximum stress in the member is 85.7 megapascal. That's it basically. The second exercise of today's lecture is similar to problem 1.9 on page 35 of the Hibbeler book. For the given structure in the picture, determine the average shear stress in the 20 millimeter diameter pin at A. So that's pin at A, and it has the diameter 20 millimeter. And also for the 30 millimeter diameter pin at B. So for this one. Looking at the picture, you can see that the pin at A is a double shear pin, and the pin at B is a single shear pin. So this is also important when you want to do the analysis. So as usual, we start with the free body diagram. So if you draw the member, essentially you have this tension from the point B, and then you have the force P here. You have two reactions at A, and then for this system here, you have three unknowns. So the tension in the cable and the two supports reaction at A, you have three unknowns, but then we can write our three usual equations to calculate those three unknowns. The usual equations are balance of forces in the x direction, in the y direction, and balance of moments with respect to any point, in this case with respect to point A. So if you write the equilibrium for moments with respect to point A, you can see that with respect to point A, the force 30 Newton is at the distance 2, and it's downward, so it wants to cause a rotation that is clockwise, but we have assumed that counterclockwise is the plus direction, so it comes with a minus sign. Then you have this force BC, which has two components. The horizontal component obviously does not cause any moment with respect to point A, but the vertical component, it causes a moment. The arm for that is 6, and also it will cause a moment that is counterclockwise. So you get plus FBC sine alpha, and that is essentially the vertical component of FBC. And 6 is the distance, and then the sinus alpha is 4/5 because of the dimensions of the triangle that you have. Okay, so this is your first equation, and it gives you FBC. So now we know FBC. the next thing you want to do is to impose the equilibrium of forces in the x direction. In the x direction, now you have AX and FBC cosine alpha. So the sum of these two must be 0, and they both appear with a plus sign because we assume that pointing towards right is plus. And that results in AX equals minus 7.5 kilonewton, telling us that the direction that we have chosen is wrong, so it's in the opposite direction. Finally, you write the equilibrium of forces in the y direction, in the vertical direction. In the vertical direction, you have AY upwards, you have 30 kilonewton downwards, and then you have FBC sine alpha also upwards. And at this point, you know what is FBC, so you can calculate AY, and that would be 20 kilonewton. Okay, so now that we have all these forces and all these unknowns, we can look into what happens to the pins. If you look at the pin at A, the force on that pin, it has two components. One component is 20 kilonewton, the other one is 7.5 or minus 7.5 kilonewton. But the magnitude of that force altogether is 21.36 kilonewton. So you can calculate the magnitude of the force, and basically that's pin A as shown here in the picture. So you have this much force for the pin to carry. But also you remember that this is a double shear pin. That means it has two sides to carry this much force, and resultant shear force would be the total force divided by 2. Okay, so the shear force on pin A on each side is the force Fa divided by 2, so half of that. Once you're careful with this, the rest is easy. The stress for the pin, the shear stress, is simply shear force divided by area, by cross-sectional area, and cross-sectional area here would be the area of that little circle, and basically that's pi r squared, r being the radius of that, or if you write it in terms of the diameter that is given in the problem, is pi over 4 d squared. And then again, the shear force for each side of the pin is half of 21.36, which is 10.68. So if you calculate that, the shear stress for pin A would be almost 34 megapascal. So that's pin A. Now we play exactly the same game for pin B. For pin B, you have the force FBC to be carried by the pin. But now, looking at the picture, you can see that it's a single shear pin as opposed to the pin A, which was a double shear pin. That means that the shear force for the pin is exactly the same as the total force for the pin. And basically, once you do that, the rest is standard. You can calculate the shear stress of the pin. The shear stress is shear force divided by cross-sectional area, and shear force is the same as FBC, that's 12.5. And then again, the cross-sectional area would be the area of the pin, and that would be pi over 4 diameter of the pin squared, and that's almost 17.7 megapascal. Okay, so basically that's it. Now we have calculated the shear stresses in both pins B and A in the previous slide. So the next topic we would like to talk about is allowable stress design. And in short, we use the abbreviation ASD for that. This topic is essentially a conceptual topic that you can intuitively imagine what that is. If you want to have a design, you can imagine that the failure load must be larger than the allowable load. So basically, you should allow for less load compared to the load that would cause failure. This is very intuitive, and basically it's this inequality. Now, in this inequality, we just assume that we know what is the failure load. I mean, it usually matters what type of material you talk about and what type of failure mechanisms you're talking about. But assuming that you know what is the failure load, then you should design the structure such that you allow for less load compared to that failure load. Now, motivated by this structure, we can construct this ratio by dividing the failure load by the allowable load, and then you end up with this factor. We call it factor of safety or safety factor, and it's shown as Fs, and that's always a number that's larger than 1, basically. Now, depending on the type of failure, you may want to think of two different failure mechanisms. Based on what we have learned so far, you can imagine that the material may fail due to normal stresses, or it may fail due to shear stresses. So if you talk about the failure due to normal stresses, then your factor of safety would be the ratio of sigma failure divided by sigma allowable, and then again sigma being the normal stress. Or you can think of the factor of safety due to shear forces mechanism, or due to the failure due to shear forces. And in that case, tau would be your shear stress. And you can imagine these two mechanisms may exist simultaneously in a structure. So obviously you should calculate both of them and design your structure for the worst case scenario. So as we mentioned, the factor of safety must be larger than 1, but maybe you can also intuitively assume that it cannot be too much larger than 1. So if you want to make it very, very large, then you would end up with a structure that may be very, very expensive and possibly not functional eventually. So based on what I just said, you can imagine that when you decide for factor of safety, there is always a trade-off that you need to take into account. And for that, good engineering insight and understanding of the problem could allow for lower factor of safety. So basically, you can have more economical design if you have a better understanding. And nowadays, we usually use computational simulations to support our understanding too. Examples of factor of safety are given here. For instance, you should know that the factor of safety for pressure vessel or for elevator is around 10 and more than 10. But then, for instance, for a space shuttle, the factor of safety is 1.4. So you can imagine that the space shuttle is a much more complex structure. So if you wanted to design a space shuttle with factor of safety 10, possibly you would end up with a heavy shuttle that would never fly, essentially, or it would not be economical for that. But also, more importantly, you should realize that a space shuttle is a much more complex structure. So when we say the factor of safety is 1.4, we are talking about the weakest part of that structure. So this is the worst part of it. So in a space shuttle, obviously you have many parts that have factor of safety much larger than 10. But the lowest part, or the lowest factor of safety, is 1.4. And basically that brings us to this point that when you think about factor of safety, you should always think about it that you need to introduce it, or we introduce it as engineers, because of unknowns and uncertainties, right? So if you know more about the analysis of the structure, then you have less unknown, you have less uncertainties, and then basically you can have lower safety factors, and they could also work. So it's always the trade-off that I mentioned. Then the more you know, the less is the safety factor. Factor of safety for usual structures can be also found in engineering handbooks and design codes. But long story short, you should design your structure based on the factor of safety introduced for that structure, and a design that is based on an allowable stress limit is called allowable stress design. So the thing that we start at the beginning, and we abbreviate that as ASD. So to do this, you always have two steps. The first step is you need to identify the most crucial part of the structure, or the most vulnerable part of the structure. And then the step two tells you that for that part, and based on the factor of safety, you compute the allowable load. So basically, again, the whole idea is that the weakest link of a chain determines its strength. So you should always think about it that way, that you should always find the most crucial part and then design for that crucial part. So I try to explain this by an example here. For instance, if you think of a simple bar and you apply a force P on that, the stress in the bar would be force divided by area, and the factor of safety for this structure would be sigma failure divided by sigma allowable. And then again, remember, sigma is the normal stress. Okay, so this is a typical mechanism that only the normal stress matters. Now you should compare this with this second example. If you think that you have these two plates on top of one another, and then you have a bolt or a pin connecting the two, and then you apply these normal forces on the two plates. Now, instead of one piece, you have two pieces. That means you need to do the analysis for two pieces. And more interestingly, it happens that these two structures, or these two parts, they are suffering, or they are subject to different types of loading or stresses. If you think about the plates, you apply a force here, so you will talk about the normal stress in the plate. But when you want to analyze the bolt, you talk about the shear stress. Okay, so basically you need to do two types of safety analysis. First, you do it against normal stress, and you do it basically for part one for the plates, and then you do it for the bolt, which is the shear stress analysis. So for the plates itself, you can see that stress is just force divided by area, and then again area here is this area. And then you calculate the stress, and basically you want, based on a factor of safety that you know, you would find the allowable stress if you know what is the failure stress, which you can find also in handbooks. Then you do the same thing for the bolt, but now for the bolt you see that the cross-sectional area is this one. So it's a star is not the same area, and then you divide the force P by that. And then again, this is more like a single shear pin. So if you had two surfaces, then maybe you need to also calculate shear stress more carefully. But in this case, that's what shear stress is. And then again, from that one, you can also calculate the allowable shear stress, or vice versa. If you have an allowable shear stress to design, you can check what is the factor of safety, and basically you need to compare the factor of safety for the normal direction or for the shear direction separately. Okay, so basically this example shows you that if you have multiple parts in the structure, then you have multiple factor of safeties. And then maybe for some reason some of them are very large, and for some reason some of them are not so large, but eventually the factor of safety for the whole structure would be the smallest number that you get. Okay, so because that shows the weakness of the structure, or the part that is most vulnerable in your design. The next exercise of this lecture is similar to problem 113 on page 51 of the book. A suspender rod, as shown here, is connected at its end by a fixed connected circular disc, as shown. So this is the disc on top, and the rod passes through a 40 millimeter hole. So there is this hole with the diameter 40 millimeter, and you are asked to calculate the minimum required diameter of the rod and the minimum thickness of the disc to support the 20 kilonewton load at the end of the rod. The allowable stresses for the rod are given, and for the disc. So the allowable normal stress for the rod is sigma equals 60 megapascal, and the allowable shear stress for the disc is tau equals 35 megapascal. So instead of giving you the allowable stresses, obviously you could have failure stresses and safety factor, but you already have the allowable ones that you can use for your design. So we start looking at the rod itself. So if you think of the rod itself, it has the cross-sectional area here as shown, and it's under normal stress. So basically for the rod, the cross-section can be calculated as follows. So you can say the cross-section is equal force divided by allowable stress. It's another way of just writing that sigma equal P divided by A, of course. Okay, so you just exchange this and you get this formula. Now, the area would be pi r squared. The force, the normal force, is 20 kilonewton. Allowable stress is 60 megapascal. If you insert that, then you end up with the radius of 10.3 millimeter, or the diameter of 20.6 millimeter. So this would be the diameter that you need for the rod itself to carry the normal stress. Okay, so we have this for the rod itself. Now we need to look at the disc part. So see what happens for the disc. Now imagine that you pull this, you pull the rod, and because you have a good design and it doesn't fail from here, it's going to carry the load all the way to the top. So now the next thing you need to make sure is that it wouldn't fail due to the shear stress that you would get at this cross section basically. So if you look at the structure you have here, the shear stress would be applied on the area as shown here. And that area you can calculate it by 2 pi r times thickness. Now r here is the radius of the disk basically. That 40 millimeter is the diameter. So you can calculate that, but then we don't know what is the thickness. So we want to know the thickness. So what you want to do is very similar to what we did before. Again, remember, shear stress is shear force divided by area. So basically you can say area is shear force divided by shear stress. Now the total shear force you have would be the 20 kilonewton, so it needs to carry all the force. Allowable shear stress was 35 megapascal, so you also put that in the denominator. Now the area is 2 pi r, which is the perimeter of that circle, times the thickness. You have r, which is 20 millimeter, and then from that calculation you can see that thickness is 4.55 millimeter. Okay, so now we have calculated the diameter, the required diameter of the rod, and also the thickness of the disc. The fourth exercise of today's lecture is similar to problem 112 on page 50 of the book. You are asked to determine to the nearest 5 millimeter the required diameter of the steel pin at C if allowable shear stress for steel is 55 megapascal. So basically, you know, the pin at C is made of steel. It's a double shear pin, and the allowable shear stress for that is 55 megapascal. For the given loads, so you have 25 kilonewton here and 15 kilonewton here. For the given loading condition, you are asked to find the diameter of the pin, and also you are asked to calculate that diameter as a multiple of 5 millimeter. So the expression to the nearest 5 millimeter, it means what is the closest multiple of 5 millimeter that would also satisfy the design requirements according to the given shear stress. Similar to our previous problems, we begin with the free body diagram. For the system, you have two reactions from the supports at C and one reaction from the support at A. At A, you have force FAB. You know the direction because the member AB is a two-force body or two-force member. So basically, you know the direction, you don't know the magnitude of FAB. For the support at C, you have Cx and Cy. So you have three unknowns. And basically using our three common equations of equilibrium in 2D, we are going to calculate these three unknowns. The first governing equation is the balance of forces in the x direction. So in the x direction, you have FAB pointing towards left. So assuming that the direction towards right is plus, you would have a minus sign here, so minus FAB. Then you have the horizontal component of the 25 kilonewton. So if this angle is alpha, that would be 25 times cosine alpha. And cosine alpha is 4 over 5. And also it points towards right, so it comes with a plus. And then Cx, it's pointing towards left, so it comes with a minus. So that's your balance equation in the x direction. In the y direction, you have Cy pointing upwards and 25 kilonewton times sinus alpha pointing downwards. So it comes with a minus sign, and 3/5 would be sinus alpha. And also you have 15 kilonewton pointing downward, so it comes also with a minus. Then you write the balance of moment with respect to C. With respect to C, you have the force FAB with the distance 200 millimeter. The rotation that the force FAB would cause with respect to C or the moment is counterclockwise, and assuming that the counterclockwise direction is a positive direction, we write this with a plus sign. Okay, so you get this with a plus. Now the force 15 kilonewton times the distance 75 millimeter, it would cause a moment that is clockwise, so it comes with a minus, so it's minus force times distance. The same holds for 25 kilonewton. For the 25 kilonewton, you have two components, the horizontal component and the vertical component. The horizontal component does not cause any moment with respect to C. The vertical component is causing a moment in clockwise direction again. The distance, the arm is 125 millimeter, which is 0.125 here, and the vertical component of the force is 25 times 3/5, and then again with a minus sign. So you have these three equations, three unknowns, and from that you can calculate the unknowns, the forces in, well, the force in AB as well as the reactions of the support at C. So what you need to do next is to calculate the shear force at the pin C. In order to do that, first you need to calculate the total force that the pin needs to carry. The total force that the pin carries is the square root of Cx squared plus Cy squared, and that gives you 30.4 kilonewton. Now, because you know the pin at C is a double shear pin, you are dealing with something like this. So basically that means the pin carries the whole force Fc on its two sides. So the force is distributed on the two sides, and basically that tells you that the shear force of the pin is half of the total force that the pin should carry on each surface. So you get almost 15.2 kilonewton for the shear force on each side of the pin. So V would be 15 kilonewton. Now, if you remember, shear stress is shear force divided by area, telling you that area is shear force divided by shear stress. Now you know what is the shear force, you know what is the allowable shear stress. From that you can calculate the area. So if you do that, the area, the cross-sectional area that you have here, so let's call it pi r squared or pi over 4 d squared. From that you can calculate d, and then you get d to be 18.8 millimeter. Now remember, we wanted this to be a multiple of 5 millimeter. That means you need to round it up so that you get the closest 5 millimeter pin. And that would be 20 millimeter. So important is that here you need to round up. Okay, so it's not just finding the approximate value close to the calculation, it's also important that you always round up in such cases. So even if you have calculated D, for instance, to be 16.2 millimeter, you should not just to find the closest 5 millimeter pin, you should not round it down to 15 millimeter, obviously. So a 15 millimeter pin wouldn't work. Also, in that case, the closest 5 millimeter would be 20 millimeter pin. Okay, so you need to always round it up such that it would carry the allowable load, basically. Exercise 5 and the last exercise of today's lecture shows a rigid bar supported as shown in the figure, and on top of the rigid bar you apply a force P. You are asked to determine the maximum P before failure. Now for this problem, the failure stresses for different parts are given. So for steel, the failure stress is 680 megapascal. For aluminum, the failure stress is 70 megapascal, and you are asked to assume that the safety factor for steel and aluminum is 2. For the pins, the failure stress or the failure shear stress is 1350 megapascal, and for that you are asked to assume that the safety factor is 3. So these are the pins, and as you can see by the figure, these are basically single shear pin if you see the side view here. The aluminum block is here on the right, and it has the cross-sectional area of 1800 millimeters squared, so you can imagine that it looks like this, and then this area is the area where it carries the load of the rigid bar, basically. So this is the aluminum cube here, and you have a steel rod here, and then you have the pins. So you can imagine you essentially are dealing with 3 parts or 3 main parts: the pins, the steel rod, and the aluminum block, and you need to design this structure such that none of them fails according to the given values for the failure stresses and the safety factors. So remember, we want to design this according to the allowable stress. So although the failure values are given here, we need to design according to the allowable values, and also remember, factor of safety is essentially the failure values divided by allowable values, or you can imagine allowable values are failure values divided by factor of safety. So in order to look at these numbers, we would transform them to allowable values. So for steel, the allowable stress would be 340 megapascal because we divide 680 by 2. For aluminum, the allowable stress, the allowable normal stress, would be 35 megapascal, which is half of the 70 megapascal. And for the pin, would be 450 megapascal, which is 1/3 of the failure value because the factor of safety is 3. So we use these ones to calculate the maximum P. Then you look at the free body diagram of the system. So basically this is your rigid rod, and then you have a force P applied here. Then you have force FAC that you don't know what is the magnitude of, but you know its direction. And then you have your reaction from the aluminum block here. Okay, you can imagine that you do not need a horizontal force to keep this in equilibrium, or if you assume that there is a horizontal force, you can write the sum of the forces in the x direction to be 0, and that horizontal force will vanish identically. So basically, you would have 2 unknowns, and you need to write 2 equations to calculate them. those two equations could be, for instance, the sum of moments with respect to point A is 0, and the sum of forces in the y direction is 0. And if you do that for this system, it's very simple. So you end up with these relations between the forces FAC and FB with respect to P. Okay, so FB would be 3/8 of P and FAC is 5/8 of P. Now, according to these three values, we will go one by one for each of the members or for each of the parts and calculate what would be the maximum P such that that particular member is safe. So for instance, if you think about this one, for the block, aluminum block that we had, for the aluminum block, the allowable stress times area would be the allowable force. Now, you know what is the allowable stress, you know what is that area, so basically you know what would be the allowable force for that, and that would be your FB. So all you have to do is to insert FB into this equation, and based on that, you can calculate the allowable force such that that particular member would be safe. So if you do that, essentially you find out that P must be maximum 168 kilonewton, such that the support at B doesn't fail. Okay, so that's that. Now we come to the next part. Thinking of what happens to the rod AC, again, you remember that the force in AC can be calculated by stress times area. You know what is the allowable stress, you know what is the area, so the dimensions are given, and from that you can calculate FAC, allowable. Okay, so this is 106.8 kilonewton. That's the maximum force that you can allow for member AC. Now, based on that force, you can calculate what would be the P, what would be the force according to that. And basically, if you do that, you end up with allowable force P to be 171 kilonewton. Okay, so if you look into the member AC, now the allowable force would be 171 kilonewton. So now we know what happens to these two. What we need to do is to look into the pins, basically. Now for the pin, the shear stress is given. So you know what is the allowable shear stress, and you know it is a single shear pin. So you multiply that by area to calculate the allowable force or allowable shear force for the pin. And when you do that, you can basically get this. So that would be 114.5 kilonewton. Now again, similar to before, all you have to do is to insert that into the relation that you have between the force and P. And then again, remember the pin is on the member AC. So the force that you are talking about is the force of AC. So you use this one. And if you use that, the allowable P that you get would be 183 kilonewton. Okay, now this is all you want. So basically you can apply maximum 183 kilonewton and the pins would be fine. But then you can see if you apply that much, then the other members will fail because their maximum force is less than that. Okay, so basically you need to find the minimum force, minimum value of the P such that all the members remain safe. And as you can see, that would be 168 kilonewton. And if you remember, that tells you that is the value that we got from the support, from the aluminum support here. So if you want, you can imagine that this is essentially the most vulnerable part of the structure. So if you need to increase this value, you need to increase, for instance, the cross-sectional area of this support. Okay, so in this lecture, we talked about the section 1.6 of the first chapter of the Hibbeler book, and that was our last discussion on the first chapter, and that was also our second and last lecture on stress. In the following lectures, we will talk about strain and then about the mechanical properties. Catch you in the next one.